Chapter 6 is about roots, ultimately. So this first section, section 6.1, it's a lot of sort of the fundamentals about dealing with different roots. So square roots and cube roots and fourth roots, that sort of thing. And there are a ton of examples in here. I forget how many there are. It's close to 30. I want to say it's 28 or 29, but that's because they're all really small. So I figure if they were so tiny, might as well just have a whole bunch. All right, so the first thing is that there's a difference in what happens depending on if you have an odd root or an even root. So first, if you have an even root, so that's this bullet point right here, then that would be like a square root or a fourth root, things like that. So if n is even, then the number under the radical, which is called the radicand, that needs to be non-negative. So it needs to be positive or 0. And that's because, at least for now, since we're not up to complex numbers yet, that's not till the end of this chapter, we're going to consider the even root of a negative number to be undefined. So like how if you're just dealing with real numbers, can't take the square root of a negative, and then you also wouldn't be able to take the fourth root of a negative or the sixth or the eighth and so forth. And also, there's that indented bullet point there that basically you have to pick a root here because, well, even just with something like this, there are two numbers that when you square them, you would get 81, right? So just from this very first bullet point, that generally if the nth root of a is equal to b, then a is equal to b to the n. When you square 9, you get 81. But when you square negative 9, you also get 81. So then when you take the square root of 81, which one do you get? So is that going to be defined as 9 or as negative 9? But by definition, that's going to be 9. So this is that indented bullet point where it's the positive root. So that's how that would work. Or if you had the square root of 16, that's going to be considered to be 4, not negative 4, that kind of thing. But then what if it's an odd root? So this bullet point right here where it says if n is odd, then a can be any real number. Well, that's because if you take the odd root of a negative, you get a negative. So like the way that that would work is that the cube root of negative 8 is going to be negative 2. And the reason for that, so that's because if you have negative 2 cubed, that's negative 2 times negative 2 times negative 2. And if you multiply the first two negative 2's together, that's a 4. So you'd have 4 times negative 2, which is negative 8. And with odd roots, there, if you take the odd root of a negative, you're going to get a negative. Take the odd root of a positive, you're going to get a positive. And you never run into that situation like you would have with an even root, where with an even root, there would be like two different numbers that you could square to get 81, like that kind of thing. There aren't two different numbers that you could cube to get negative 8. The only one that works is negative 2. And I guess really the term that would fit the best here would be that there's a one-to-one correspondence when you have an odd root. Where when you're taking the odd root of a number, there is one number that you could raise to that power to get that radicand. So when you have an odd root, things in a way end up being simpler, even though there are more possible values. Doesn't seem like those should go together, but they kind of do. All right, so then evaluating these expressions. So the cube root of 27, for that you would want the number that if you cubed it, you would get 27, and that's going to be 3. And that's since 3 cubed is equal to 27. The fourth root of 256. All right, well, we're not really dealing with irrational numbers here, so it's going to have to be something. I guess you can kind of start cycling through them. 2 to the fourth power, that's going to be 16. 3 to the 4th power is going to be 81. And then 4 to the 4th power, that's it. So this is going to be 4. And that's since 4 to the 4th would be equal to 256. And if you don't see it right away, I guess you could start cycling through them. So you could say, like, this is kind of off to the side, which is why I've got it a different color, but 2 to the 4th, that would be 2 times 2 times 2 times 2. So I guess you could say, well, it's 4 times 4, which is 16, not 256. 3 to the 4th, I guess you could get crafty here. You could use that one law of exponents and say that's 3 squared, which is true. But I'll just write it all the way out. So like 4 3s multiplied together, that's 81. But then 4 to the 4th, that'll do it. Because then if you have 4 4s multiplied together, that's 16 times 16. So that's 16 squared, which is 256. And that multiplication symbol doesn't look so good. All right. Draw. There, it's a little better. Okay. Then the next one, the cube root of negative 125. So that should be a negative, and more specifically, it's going to be negative 5. And that's since negative 5 to the 3rd power would be, well, it's negative 5 times negative 5 times negative 5, which is 25 times negative 5, which is negative 125. All right, then the 4th one we actually can't do. So this one right here, this is not a real number. So we can't take the even root of a negative and get a real number. That's not going to work. You can get an answer to that if you use complex numbers, or imaginary numbers, I suppose. So like if you're using the complex number system instead of the real number system, you'd end up with 2 times radical I. But for now, we're not going to worry about i's and complex numbers. So let's see. Then simplifying expressions of the form nth root of a to the n. So if n is even, then we're going to say that the nth root of a to the n is the absolute value of a. But if n is odd, then that's just going to be a. And that's because when you're taking an odd root, you can have negatives. So that's why there's that difference there. When you're taking an even root, we'd already said that the accepted practice is to take the positive square root. So we've already kind of seen this idea, right? Like if you have the square root of 64, you consider that to be 8, right? So that's the positive, and that's what you get if you took the absolute value. But then just to run through these real quick, so 5th root of z to the 5th, that's an odd root, so that's just going to be z. 6 4th root of n minus 3 to the 4th, so we need the absolute value. So absolute value of n minus 3. Number 7, that negative is actually out front. So that's going to be the negation of the absolute value of negative 2. But the absolute value of negative 2 is 2, so that's really just negative 2. And then number 8, let's see, I guess there are a couple different ways that you could view number 8. I need a little bit of extra space here. All right, so number 8, you could say, well, that's the cube root of 3 cubed over 2 cubed, or the cube root of 3/2 cubed. So then that's just 3/2. Right? It's the absolute value of 3/2, but that's just 3/2. Or you could break this up. So I guess let me do this in a different color maybe. So let's say, or you could rewrite that as the cube root of 27 over the cube root of 8. And so it's going to be 3 over 2, right? Either way. So there are a couple of different ways to arrive at the right answer. And I said something about an absolute value here a second ago. That's an odd root. So forget I said it, right? Absolute value only goes with even roots. So sorry about that. I was kind of looking at 6 while talking about 8 and threw myself off. All right, so then the next thing, this ends up being really helpful later, being able to switch between radical notation and exponential notation. Sometimes going one way, sometimes going the other way. So you could write the nth root of a generally as a raised to the power of 1 over n. Sometimes it helps going left to right. Sometimes that helps going right to left. So let's see what we got with these here. So 16 to the 1/4, you could write that as the 4th root of 16 if you write it with a radical. And the 4th root of 16 is going to be 2. 8 to the 1/3 power, you could write that as the cube root of -8. And so then that's just going to be -2. 11 and 12. So there's something to watch out for here. So with no parentheses with 11, that negative sign is out front. So the only thing that's being raised to the 1/2 power is the 81. So you would end up with the negation of the square root of 81, but the square root of 81 is 9, so this is -9. With 12, with the parentheses, then the -81 is being raised to the 1/2 power. So that's going to be the square root of -81, and that is not a real number, since that's an even root of a negative. So that's not going to be a real number. And then the last one with 13, we could rewrite that as the 5th root of p. So I wanted to have one just with a variable in it, because we're certainly going to see a bunch of that in the future. 14 and 15 are going the other way. So instead of having it written with a radical, to rewrite it so you have a rational exponent. So if we have a cube root, we can write this as 9x raised to the power of 1/3. I guess the one thing to watch out for with something like 14 is just to make sure you're raising the entire 9x to the 1/3. So put the 9x in parentheses, because without the parentheses, the only thing being raised to the 1/3 would be the x. And you need the whole 9x. Then with 15, we're going to do the same kind of thing. We want to raise that whole expression under the radical to the 1/4 power. So I'm going to put a cubed b over 7 in parentheses, and we're going to raise that to the 1/4, like that. And that 4 doesn't look so great. It looks like the top part's kind of closed up. It's a 4. I don't know why that's not turned out so well. Okay, then next thing, evaluating expressions of the form a raised to the power of m over n. The book has this written in the opposite order, but either one would work. So either you could do the nth root first and then raise to the m power, or you could raise to the m power and then take the nth root. I would stress this one, which is why I wrote it first, because if you take the nth root first, then you tend to have smaller numbers to deal with. So I'll show you what I mean. Even with this 9 to the 3/2, we'll be able to see it. So I'm going to write this as the square root of 9. And the reason this works, by the way, so I think this is actually worth writing out before we even get to that. Really what I'm going to do is I'm going to say this is 9 to the 1/2, then cubed. So where there's that one law of exponents, where if you have a power to a power, you can multiply the powers together. Basically, I'm undoing it there. And I'm saying, okay, well, I'm going to raise 9 to the 1/2 and then cube it. We're going to go step by step instead of all at once. But then the 9 to the 1/2 is the square root of 9, right? So we're going to have the square root of 9 cubed, but the square root of 9 is 3. So this is 3 cubed, which is 27. Simple enough. What if you go the other way? So if you go the other way, then you would have 9 cubed to the 1/2. Right, we can do that. So then I guess that means we could rewrite this as the square root of 9 cubed. 9 cubed is kind of a big number. It's 729. So that's the square root of 729. And that's one that's hard to remember, that's actually 27. But you would get the same answer. Although I tend not to do it this way because you get those big numbers. If you take the root first, you'll keep the number small. So I think that's the way to go. So I would do that right there, that first way. Because if you look at that, the numbers never get big, right? It's a 9, you take the square root, it's a 3, you cube 3, 27, right? They never get huge. But then in that second one, they kind of do, right? 9 cubed is a big number. And then it's a lot harder to see what that square root's going to be, right? Because that's not one that you see all the time. And so it makes it tougher to figure out. So that's how I would handle those. And even with the rest of these that are here, that's exactly how I'm going to do them. So the 125 to the 2/3, I would think of that as being the cube root of 125, which is then squared. And the cube root of 125 is 5, so that's 5 squared, which is 25. And this one you could really see it. If you did it the other way, you'd have to square the 125, whatever that is, and then take the cube root. So that seems a lot harder. 18, so with 18, that negative is out front, right? It's not that you're raising negative 36 to the 3/2 because there aren't parentheses. So that negative just stays out front. And we're going to have the negation of the square root of 36, which is then going to be cubed. So square root of 36 is 6. So it's going to be the negation of 6 cubed. But then 6 cubed is 216. So this is negative 216. 19. So again, root first. So here the negative 27 is being raised to that power. So when I write this out, I'm going to have the cube root of negative 27, which would then be raised to the 4th. And the cube root of negative 27 is negative 3. So you have negative 3 to the 4th, which works out to be 81. Because if you have 4 negative 3's multiplied together, then it would be like having 9 times 9, which is 81. Number 20 we're not going to be able to do. Because here, if we try to rewrite it, we're going to have the square root of negative 36 raised to the 7th. But the square root of negative 36 isn't a real number, so we can't simplify this thing. So that right there, that is not going to be a real number, since the square root of negative 36 is not a real number. So that's the problem. If we can't do that, then we couldn't raise it to the 7th. So that's where we get stuck. All right, then let's see. The next few are rewriting expressions with rational exponents. Okay, so it's kind of like what we're just doing, but maybe a little bit different. So we can view taking the 5th root as raising to the power of 1/5. So we could write this as x cubed to the 1/5. And then if we have the power raised to another power, we can multiply them together and say that that's x to the 3/5. And we're going to do a similar thing with these other ones too. So 22's got a 2 out front. I guess really that's just going to stay there in this case. So we're going to have 2 times a squared to the 1/3. But then that'll be 2a to the 2/3 when we multiply those exponents together. 23, it looks like we've got a lot going on under the radical, but let's see what we've got. So inside the parentheses, which I guess I'm going to have to write this with brackets. I'm going to need 2 sets of grouping symbols to get this to look right. So we've got 24xy squared to the 1/3, and then that's going to get raised to the 4th. We do have a power to a power again, so we can multiply them together and say that what we've got is 24xy squared to the 4/3. All right. Then the next thing is if you've got negative rational exponents. We've seen negative exponents before because that was one of the laws of exponents that we had. So basically, it's if you've got a negative exponent and it's in a numerator essentially, then if you bring it down to the denominator, you can rewrite with a positive exponent, and going the other way around. If you have a negative exponent in a denominator, if you bring it up, then you can write it with a positive exponent. So that's what we're going to do here. So it's something like 49 to the negative 1/2. Bring it down. So we're going to have 1 over 49 to the 1/2. Or if you want that written with a radical, 1 over the square root of 49. The square root of 49 is 7. So this is going to be 1/7. Then with 25, that's one where you got the negative exponent in the denominator, so bring it up. And you could rewrite this as 64 to the 2/3, which I would do the root first and say cube root of 64, figure out what that is, and then square it. So the cube root of 64 is 4. So we're going to end up with 4 squared, which is 16. Then number 26, got a negative exponent that we got to bring down. So we could write this, I guess, as 3 times 1 over x to the 3/4. But then, again, the 4 just turned out really badly there. So 1 over x to the 3/4, which then we could multiply those together and say that's just 3 over x to the 3/4. All right, that looks a little cleaner. Again, that 4 is messed up, but it's a 4. So 3/4 in that exponent in the denominator. All right, using a calculator. So far we haven't had anything where we were taking a root and it didn't work out to be an integer. These are not going to be integers. Because 17 is not a perfect cube. 53 is not a perfect 4th. So we're not going to get integers here. It depends on what kind of calculator you have for what you'd have to do here. There are some brands of calculator that will allow you to specify the root that you want, but for some it's kind of difficult to do. Specifically, if you have a TI calculator, it's easier to rewrite with a rational exponent and do it like that. So what I would do here, and this will actually work with ones where you do have a button where you can specify the root as well. But there it is, admittedly, probably easier to specify the root, but I think this is a more universal way of looking at it. If you rewrite this with a rational exponent, it would be 17 to the 1/3. So what you would do with a calculator is that you would have 17, and you're going to have a caret button that looks like that somewhere, and then put the 1/3 in parentheses, so that way you're raising to the 1/3 power, not raising to the first and then dividing by 3. And what you get here is roughly 2.57. It carries out a lot farther than that. Since it's an irrational number, it'll carry on forever. But to 2 places, that's what it is. So this sort of thing, and I'll just change colors real quick. But this, like with a TI calculator, this is what I would do. If you have a Casio, depending on what model you have, you might have one where you can specify the root. And actually, I don't know where my TI that's in the 30s range is, because if you have a TI with a model number in the 30s, those are the business calculators. They may have a root key. I don't remember. But since I've moved, I haven't found that calculator. So I don't know where it is right now. But that may exist. If you got one in the 80s range, though, if you got a graphing calculator, you got to do that thing that's in the red box. So then it would be a similar thing with 28. I would think of that as being 53 to the 1/4. So then with a calculator, you could write that as 53 and then caret and then put the 1/4 in parentheses. So you could do it like that, or you could do it as 53 caret 0.25. Since that's a terminating decimal, you could write it out like that. And this ends up being roughly 2.70. At least that's what it is to two places. And then the 39 to the 3/4. This is one where even if you have a root button, you might want to just use the rational exponent. I think you would. And just to say, well, then this will be 39 raised to the power of 3/4 and put the 3/4 in parentheses like that, or 39 raised to the power of 0.75 if you want to write the 3/4 as a decimal. Either way should work, and what you get roughly is 15.61 to two places. So using a calculator, I think that is what I would suggest, is to use rational exponents generally. Although if you have the luxury of having a root button where you can customize your roots, you can certainly go ahead and use it. But even for something like 29, even if you have that button, I would probably use the rational exponent there.